given, in this what happens is that if I have to draw a line which separates these, I can just draw over here. This could be one of the possible lines, or this could be one of the possible lines. Okay. Or I can do a non-linear function as well, right? I mean, I can say, hey, this is one of the possible lines I want to do. See, I mean, so each of these is a hypothesis. That, I mean, when I say I'm drawing a line, it means it's a function. uh, Graphically, when I say a line, algebraically, I'll say it's a function, right? So a hypothesis is, hey, given a set of some stuff or set of some data points, right? It is a function which can describe the graph, or which can describe the best possible way to describe the data points, right? And there is not a function, but it can be a set of functions, right? I mean, if you see the equation of this function, sorry, the equation of this function is clearly different from an equation of this function. Yet, it still, to some extent, describes the data points, right? Or this can be a different function. It's a nonlinear function for all you know, right? So each and every one of these set of functions which describes the data set which we have is called each function is called as a hypothesis. And I use the term also a hypothesis space, right? And I use the term hypothesis space, which means it's a set of all functions, set of hypotheses, or set of all possible hypotheses. Okay, so this is in a way, what hypotheses means. Okay, it could be a single function, or it could be a bunch of functions which can best describe this data set, and each of those functions are called as a hypothesis. Now, going back to our Bayes theorem here, right? Generally, we use a capital H, and we use capital H to represent a set of hypotheses, and a single, lowercase h to represent a hypothesis. Okay. Now, if we go ahead and write our Bayes theorem for these, what is the probability that a given hypothesis is correct or yields a good result among the set of hypotheses is given by, as again, just let's apply the probability divided by P of D. This is simple, plain and simple Bayes theorem. Now, that means, hey, I've been given a data set, and I want to find out, hey, I have a hypothesis, which means I have a function which best describes a particular data set. Then what is the probability that is the hypothesis I am looking for? Or what is the probability that one is the best and not something else among the set of all possible hypotheses in the space? Okay. In order for us, in order to find that one out, in order to find whether, hey, if it is indeed the hypothesis which we are looking for, or the function which we are looking for. So I'll keep interchangeably, I'll keep function and hypotheses and function and hypotheses. Well, think of it almost they're similar, and I'm deliberately doing that. I'm deliberately switching by using hypotheses and function, just so you understand that both of them means the same. So the probability that a function best describes the data set is what is written over here. Now, but there are other functions as well in the hypothesis space, right? So is the function which I have chosen is really what it is best describing? Okay, and in order for me to tell that, the probability must be higher. As simple as that. So which is where we use maximum a posteriori hypothesis. Okay, or in simple terminology, map hypothesis is what we call. Okay, where we describe the hypothesis map as argmax of the posterior probability. Now, what is this? Where H belongs to that. What does argmax means is, think of it like it's another function over a function. Now, let's say I have a function f of x, and I will do a argmax of f of x. Then it will give me the argmax function gives me the value of h, or value of x, where f of x reaches maximum. Okay, so this is what argmax means. So it gives me the value of h where the hypothesis is maximum. And that is what map hypothesis is all about. Okay, where you will get to know the you'll get to know the maximum where the probability of a particular hypothesis is high, or the date given a data set. Now, a couple of things I want to note over here. So I have a set of hypotheses. I can, it's all by experiment, because as you know, this is a supervised learning methodology. It's not unsupervised or anything. It's a supervised learning methodology. So which means we know what the final class is all about, and so then, hey, we will have to first, instead of just directly calculating the probability, we will instead, in order for us to find the graph which suitably fits which suitably fits the hypothesis, we need to start with something, which is where we generally assign, or we with an assumption that they are equally probable. That means if I have a set of function in hypothesis space, before I go ahead and do a calculation at all, what we basically do is we assign equal probability to all of them. Which means, so let's say I have mod of h, which means the number of hypotheses I have for a given data set. Okay, so what I do when I do a probability distribution, I assign the equal probability to all of them. Then I'll start feeding in some model, designing some model onto that, and then see how well it is, you know, how well it is responding, how well the model is getting built and responding on top of it. Okay. Now, what happens is that if the data is, and there are a couple of things which you have to remember over here. Okay, the training data, it should necessarily be noise free. Okay, and then there should be no prior reason to believe that hypothesis is, there should be no response, there should be no relationship between each of the hypotheses, which means, let's say I have a function h1 and I have a function h2, there should be nothing else which should say that these two are related in any way. That means they're mutually independent. Okay, mutually independent functions. That is, which is where I can assign an equal probability to each of the functions which are representing the data set. Okay, if the data which has given to us, if the data which has been given to us is inconsistent, which means it's inconsistent with whatever the function which I have been representing. What do I mean by that? Let's say if I feel that this is the best line, which this line is the best which is representing the data which I have, but indeed it is not, then the data says it is not, or the training model says it is not, at which point, or it is that h becomes inconsistent, or the function or the hypothesis become inconsistent with d, at which point the probability of h is most probably 0. Okay. At the same time, if it is indeed representing the if it is indeed representing the hypothesis, or if the hypothesis is indeed representing that particular data which we have, or which means it is consistent with the d, okay, then it will at least be 1 by the subset of these hypotheses. Let's say the subset of these hypotheses as vs are the number of subset of these hypotheses. So I can have, so what does this conclude, or what am I telling here? Given a data set, I can have n number of hypotheses, n number of possible hypotheses or possible functions which can represent a data. Not all of those functions are supposedly consistent. There can be inconsistencies among those functions which are representing the data. For those functions which are inconsistent, the probability of them would be 0. Okay. And those subset of functions which are indeed consistent with the data, which means it is represented, that function is representative of those data set, the probability of them will be at least 1 by the number of that subsets which is representing those particular hypotheses. Okay, and so this is what this is where the map hypothesis would be really helpful. In a way, we will get to know what is that maximum point, or what is that point when we use argmax, right? I mean, what is that value of that h which will, where that whole probability reaches the maximum. That is the value I'm going to choose, or that's the function which I'm going to choose. Okay. So any clarifications at all in what I explained? I tried to put it as much small as possible, or as much detail as possible, with less mathematics and less explanations, but any questions at all? Until now, whatever I explained, what's the meaning of an hypothesis, hypothesis space, what's map, what is that, argmax, and what can be a given hypothesis could be consistent or could be inconsistent. Okay. Okay. So now, as again, whenever there is a function, uh, whenever there is a function or set of functions which are representing certain data points, right? So an analysis need to be done on the error rate of errors with respect to a particular hypothesis, right? I mean, that is where the error calculation is where we do it, right? So that is where we say we use this maximum likelihood hypothesis, or which could lead to least square error hypothesis. But I'm going to explain about what is a maximum likelihood hypothesis first, and we'll just derive the okay. So what is the maximum likelihood hypothesis is when I take the square of an error, okay, between the actual output and the training data which we have, that is what we call it as the maximum likelihood hypothesis, or in other words, least squared error hypothesis is also what we call it. Is that okay? So whenever I say if the square of the the square of the error between the output hypothesis with what my training data is talking about, okay, that is where we call it as the maximum likelihood hypothesis. And in this, when I have a bunch of functions, and I want to find out what is the maximum likelihood that a given function has a least squared error, okay, and it all comes to this probability density function, or in other words, normal probability distribution. And normal probability distribution, which is represented by a bell curve. And I'll also give you the equation of the bell curve. But let me tell you a simple, or whenever we say normal probability distribution, people get a lot confused about it. And let me give you a layman example of this, or not even a layman example, forget it. I'll give you an example. It's an engineering example. And think of what is the meaning of normal distribution, or try to extract the meaning of normal distribution out of it. And let's put it back to this one and why it is, what is the equation and things like that. One of the assignments which we had when I was doing my master's was, a robot. One of my class was robotics. A robot in a given grid has to reach a goal in shortest possible way, and these are all obstacles. Okay. Now, the robot, R is the robot and G is the goal. The robot has to reach the goal. Hey, we have seen so many graph algorithms and of the shortest path algorithms and all of those. But when it comes to robotics, right? And when I turn on the robot, and let's say for example, robot has a map. Robot has a map, but the robot doesn't know where exactly in the map it is placed. Okay, just because the robot has a map on what the obstacles are and what the goal are doesn't necessarily mean the robot knows where it is. It has to deduce out of some parameters where it get. So when we switch on the robot assumes that it can be anywhere in the map. It can be next to goal, it can be very far from the goal. It assumes everywhere. The probability is equally distributed. That is what we call it as a normal probability. The probability that I am at a given place is equally distributed. Then, subsequently, when robot starts to learn stuff by looking or by having the sensor definitions, range sensors and all of those, which could be when by the combination of what's in the map versus what is the sensor data we are getting, that's when the probability of if it is going to change. But the concept what I'm trying to tell is the normal probability distribution when the robot switches on, it it assumes that it could be anywhere in the map, which is where we call this as a normal probability distribution, saying that I can be anywhere in the map. But as and when it starts to learn, that's when the normal probability distribution goes away and tries to get the actual probability. So similarly over here, whenever I have a bunch of hypotheses, I will start with, okay, all of them could have an equal probability of maximum likelihood. Okay, only when I start feeding the training data to those stuff, which is when I will get to know, hey, what is the probability I'm reaching to, or what is the function which is giving me maximum, or the least squared error among these, and what function I need to choose for. Hopefully, I have given enough example to think about, what does normal distribution means, and in a less mathematical way, and and then we'll talk about the rest of the stuff. Any questions on this explanation? Okay. Now, indeed, if you think about it, right? I mean, when I'm when I say probability of hypothesis given D is equal to probability of D given H times probability of H divided by probability of D. Okay. Well, the term which affects the most in this particular equation is this terminology. That means, hey, what is the probability that this data happens given this hypothesis? Okay, what is the probability that this data happens given that hypothesis? So, so when we assume a kind of mutually independent fixed training set, I can write that the hypothesis of maximum likelihood is argmax of all the hypotheses in a given hypothesis space. Okay, the uh, probability of the given hypothesis, a probability of all the attributes given a particular hypothesis. Or in other words, I can say, hey, I have m data in it. So then I will say it's a product of I going from 1 to n, the probability of d of I given h, because this I can divide it into n number of data samples, right? Now, fine. Now, this is initially a normal distribution. And what is the formula for normal distribution? The formula for normal distribution is 1 over square root of 2 pi standard deviation e to the power minus 1 over 2 standard deviation into x minus mean square. Okay, so did I mistake anything over here? Is this right, ma'am?
Yes, sir. R minus correct, sir.
Okay, so this is my normal distribution or Gaussian distribution formula. So now substituting it over here, product over everything, it is 1 over square root of 2 pi sigma square e power minus 1 over 2 sigma square times over here, the thing is di minus, I'm just going to write the mean value will still be one of the values over there. Okay, one of the values among it. So I'm just going to say h of either h of I or h of x of I square. Sorry, I'm just going to shift this whole stuff over here. Sorry about that. Now this is the max. This is the calculation for maximum likelihood. Now let's simplify this. This is a lot cumbersome over here. So I'm just going to copy the same thing over here. Okay, 1 over square root of 2 pi sigma square e power minus 1 over 2 sigma square di minus the mean of error is the hi square, which means, okay, now I want to simplify this. I'm not liking this. Okay, now if I, going back to mathematics, if I got to convert this product into sum, we use our famous logarithms. ln is log to base e. I'm sorry. Log to base e is ln. Okay, and why do we worry about logarithms here? because of a simple logarithmic fact, is log of a into b is equal to log a plus log b, right? Because of this simple fact, if I need to convert any product into summation, then all I got to do is do a logarithm. So this is an into. So then what happens is argmax, where h belongs to hypothesis space, summation I, okay, now logarithm of 1 over square root of 2 pi sigma square times logarithm of something to e, it's again what is that, log to base a of a power b equal to b, right? So b times log to a is, this becomes 1, so it's b. So the same way over here, so if I apply this formula over here, then all I get is, I'm sorry, minus 1 over 2 sigma square di minus h of x of I whole square. Okay, now this is given a hypothesis, standard deviation is constant, so I'm just going to eliminate it out of summation. It doesn't have a lot of effect, right? Eventually I'm just going to even try to eliminate this, but let me do it step by step. So I'm just going to eliminate it as constant. Okay, and it becomes 2 sigma square di minus h of xi whole square. Now you see the minus over here is pretty significant. If I'm doing a summation over a difference or minus, and if I am, if I'm trying to find the maximum of it, that means it is indeed a minimum of it. Okay, the minus actually makes a lot of difference, which is why instead of saying argmax, I'm just going to say argmin, which is the minimum value of a given function. One over 2 sigma square di minus h of x of I whole square. Again, like I said, this is another constant. So the maximum likelihood hypothesis is argmin among the hypotheses, summation of I going from 1 to m, where it is all of the hypotheses, all the elements in hypothesis space. Okay. So what is this telling me is that the maximum likelihood hypothesis, the hypothesis which has argmin, you see this is minimum, I'm using argmin, which has the minimum least squared error. As simple as that. I did so much of math, but all it is telling is, hey, the one with the maximum likelihood, what is the maximum likelihood hypothesis telling me is the one which has the minimum least squared error. Okay, so which is what we just derived here. Any questions at all? I told you two hypotheses. One is a map hypothesis, and another one is, maximum likelihood hypothesis. To find out what is that function which gives you, or which is representative of the data set which you get. Any questions at all? Okay, if we do not have any questions, then I will wrap this one up. Hopefully, you understood whatever I told. I know it's more mathematical, but hopefully, you just go through once your textbooks is good. Probably, I would give you know it's not you wouldn't get it in the first shot, but with all the background which I just gave on what a hypothesis mean, what is a normal distribution, with all that background, just try to read through what's there in a textbook. I think you should be able to understand to a fair level as to what they're talking about.
Yes, students, any doubts, any clarifications, you can ask. Okay, sir.
Okay, thank you very much and have a good rest of the day.
Thank you, sir. Good day to you too.
Thank you.
Thank you, students.